Tonight we're going to talk about something that sounds like humanity's greatest adventure but might actually be our most dangerous delusion. We're going to explore the terrifying problem with colonizing Mars. Not the inspirational version you see in movies or the optimistic promises you hear in the news, but the actual brutal physical reality of what it would take to live on another planet. Because here's what most people don't understand. The problem with colonizing Mars isn't just about building rockets or growing food. It's about fundamental physics, chemistry, and biology that we can't engineer our way around. And by the end of tonight, you're going to see why the dream of making Mars our backup planet might be built on foundations that simply don't exist. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start with what everyone knows. Mars is the fourth planet from the Sun, sitting about 49 million miles farther out than Earth. That's roughly 142 million miles from the Sun, or 228 million kilometers, compared to Earth's 93 million miles. It's a cold, red desert world about half the size of Earth, with a diameter of roughly 4,200 miles, compared to Earth's nearly 8,000 miles. Its surface area is about equal to all of Earth's land area combined, which sounds promising until you realize that all of that surface is hostile to human life in ways that nowhere on Earth, not even Antarctica or the deep ocean floor, can match. Mars has an atmosphere technically, but calling it an atmosphere is generous. The pressure at Mars's surface is about 0.6% of Earth's atmospheric pressure. To put this in perspective, Earth's atmosphere at sea level exerts a pressure of about 14.7 lb per square inch. Mars' atmosphere exerts about 0.09 lb per square inch. That's roughly the same as the atmospheric pressure at 100,000 foot above Earth's surface, which is well into what we consider space. The Armstrong limit, the altitude above which water boils at human body temperature, is about 62,000 foot. Mars' entire surface exists well above this limit. This means that if you stepped onto Mars without a pressure suit, the liquids in your body would begin to boil. Not because Mars is hot, it's actually freezing, but because at such low pressure, water vaporizes at body temperature. Your blood wouldn't literally boil in your veins because it's contained in a pressurized system, but any moisture on your tongue, in your eyes, or in your lungs would immediately start to bubble and evaporate. You would lose consciousness within about 15 seconds due to oxygen deprivation. Your body would swell as gases expanded in your tissues and you'd be gone within 2 minutes. This isn't speculation. We know exactly what happens to unprotected humans in near vacuum conditions, from a handful of accidental decompressions in space program history. The Mars atmosphere is 95% carbon dioxide with about 3% nitrogen and about 1.6% argon. There's virtually no oxygen, just trace amounts of about 0.13% for comparison. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and less than 1% argon, with only about 0.04% carbon dioxide. You can't breathe Mars's atmosphere. It would be like trying to breathe car exhaust in a near vacuum. Even if the pressure were higher, the composition would kill you. But the pressure isn't higher. It's almost non-existent. And this creates cascading problems that affect every single aspect of potential colonization. The temperature on Mars varies wildly. At the equator on a nice summer day, temperatures can reach about 70 degrees F or 21 degrees C, which sounds pleasant, but that's the peak at noon at the warmest spot on the planet on the warmest day of the year. At night, temperatures at the same location drop to about 100 degrees or 73 degrees C. That's a temperature swing of 170 degrees in a single day. The average surface temperature across the whole planet is about 80 degrees F or 62 degrees C. That's colder than Antarctica ever gets. Living in this environment would require constant heating. Not like turning on a heater when it gets chilly, but requiring massive amounts of energy just to keep habitats warm enough that equipment doesn't freeze and crack. Water freezes at 32 degrees F or 0 degrees C or 0 degrees C. Mars is routinely 3 times colder than that. This means any water, any liquid, any biological system would freeze solid unless actively heated. And heating requires energy. Vast amounts of energy continuously forever. The thin atmosphere also means there's almost no insulation. On Earth, our thick atmosphere acts like a blanket holding heat and moderating temperature swings. Mars' whisper-thin atmosphere provides almost no buffering. Heat radiates away into space almost instantly. This is why the temperature swings are so extreme. When the sun is up, some heat arrives and the surface warms slightly. The moment the sun sets, that heat radiates away and temperatures plummet. There's no atmospheric blanket to hold it in. Building habitats that can maintain livable temperatures in this environment is technically possible, but it requires constant energy input and perfect insulation. Any crack, any seal failure, any loss of power and the habitat freezes, or the air leaks out, or both. Now let's talk about radiation. This is where the real danger begins. Earth is protected from space radiation by two things, our magnetic field and our atmosphere. The magnetic field generated by Earth's churning liquid iron core creates a protective bubble around the planet called the magnetosphere. This field deflects most of the charged particles streaming out from the sun, the solar wind preventing them from reaching the surface. The atmosphere provides additional shielding, absorbing radiation that does make it through the magnetic field. Between these two layers of protection, radiation at Earth's surface is minimal. You get a bit from cosmic rays, a bit from natural radioactivity in rocks, but nothing dangerous under normal circumstances. Mars has neither of these protections. Mars used to have a magnetic field billions of years ago when its core was still molten and churning. But Mars is smaller than Earth and it cooled faster. The core solidified, the magnetic field died, and without that protection the solar wind gradually stripped away most of Mars's atmosphere over the next billion years. Today Mars has no global magnetic field, just some small patches of magnetized crust in the southern hemisphere, remnants of the ancient field, providing essentially no protection. And as we discuss, Mars's atmosphere is less than 1% the thickness of Earth's. This means radiation from space hits Mars's surface almost unimpeded. Astronauts on the International Space Station, orbiting inside Earth's magnetic field but above most of the atmosphere, receive about 50 to 2,000 millisieverts of radiation per year, depending on solar activity. For comparison, the average person on Earth receives about 2 to 3 millisieverts per year from background radiation. A chest X-ray gives you about 0.1 millisieverts. A CT scan might give you about 10 millisieverts. The annual dose limit for radiation workers in most countries is about 20 millisieverts. Astronauts on the ISS receive 50 to 100 times more radiation than people on Earth. On Mars' surface, it's worse. Measurements from NASA's Curiosity rover show that the radiation dose on Mars' surface is about 24 millisieverts per month during solar minimum periods. That's about 290 millisieverts per year. During solar maximum periods, when the sun is more active, the dose increases. And during solar particle events, massive bursts of radiation from solar flares, the dose can spike dramatically. A single large solar particle event could deliver a dose of several hundred millisieverts over the course of a few hours. Let me put these numbers in perspective. The evacuation level for areas around the Chernobyl disaster was 50 millisieverts for the first year after the accident. People receiving more than that were told to leave. The dose that causes acute radiation sickness, where you start to feel sick within hours or days, is about 1,000 millisieverts received over a short period. The dose that has a 50% chance of being fatal within 30 days is about 4,000 to 5,000 millisieverts. On Mars, without shielding, you'd about 290 millisieverts per year under normal conditions. That's nearly 15 times what radiation workers on Earth are allowed. It's 6 times the Chernobyl evacuation threshold, every year, continuously. Forever. The health effects of chronic radiation exposure at these levels are well documented. Increased cancer risk is the most obvious one. For every 100 millisieverts of radiation dose, your lifetime cancer risk increases by about 0.5%. On Mars, receiving 290 millisieverts per year, your cancer risk would increase by about 1.5% per year. After 10 years, assuming the effects are roughly additive, you're looking at a 15% increase in lifetime cancer risk. After 20 years, 30%. This is in addition to your baseline risk, which is already around 40% over a lifetime for most people. So instead of a 40% chance of getting cancer at some point in your life, you'd have a 55% chance after 10 years on Mars, a 70% chance after 20 years. But cancer is actually one of the less immediate concerns. Radiation damages DNA in all cells, not just those that might become cancerous. It causes cataracts in the eyes, clouding your vision over time. It damages the cardiovascular system, increasing risk of heart disease. It affects the brain and nervous system. Recent studies of astronauts who've spent long periods in space where radiation exposure is much lower than on Mars' surface show concerning effects on brain tissue. Radiation exposure appears to accelerate cognitive decline, affect memory and decision-making, and may contribute to increased rates of neurodegenerative diseases later in life. These effects become more pronounced with higher doses. Radiation also affects fertility. Both sperm and egg cells are particularly vulnerable to radiation damage. High levels of radiation exposure can cause temporary or permanent sterility. And even if colonists remain fertile, radiation damage to reproductive cells could cause genetic mutations that would be passed on to children. The risk of birth defects increases with parental radiation exposure. Now you might say, you can shield against radiation, build habitats underground, or pile dirt on top of structures. Yes, that helps. Radiation shielding is possible, but it's not a simple problem to solve. To reduce radiation to Earth-like levels, you need about 3 melon or roughly 10 foot of Mars soil called regolith on top of your habitat, or equivalent shielding from other materials. 3 sets of regolith is heavy. Mars regolith has a density of about 1.5 g per cubic centimetre. 3 m of it covering a habitat weighs about 500 kg per square metre. That's about 9,000 lb per square metre. For a modest habitat with a floor area of 100 square metres, about 1,000 square feet, you need to pile 450,000 kg or about 500 tons of regolith on the roof. And that's just the roof. The walls need shielding too. Moving 500 tons of dirt is a major construction project even on Earth with unlimited equipment fuel and workers. On Mars, with limited equipment, no fuel infrastructure, and a tiny crew wearing cumbersome spacesuits, it becomes enormously difficult, and this assumes the habitat structure can support that weight. Building a structure strong enough to hold 500 tons of dirt on its roof while also maintaining internal pressure against the near vacuum outside, while also being airtight and thermally insulated, is an engineering challenge orders of magnitude beyond anything we currently build. Some designs propose building underground, instead excavating caves or lava tubes. This solves the shielding problem if you can find a suitable cave, but it creates others. Excavation on Mars is difficult. The regolith is full of perchlorates, toxic chemicals that corrode equipment and are dangerous to humans. The dust is incredibly fine, smaller than talcum powder, and electrostatically charged, meaning it sticks to everything. Every piece of equipment, every spacesuit, every seal and joint would be constantly contaminated with this fine, abrasive, toxic dust. Keeping it out of habitats would be nearly impossible. On the Apollo missions to the Moon, which only lasted a few days, lunar dust was one of the biggest problems. It got into everything despite extensive precautions. It scratched helmet visors, degraded seals, caused breathing problems when tiny amounts were brought inside the spacecraft. Mars dust would be similar, except the missions would last years, not days, giving the dust many more opportunities to cause problems. And unlike lunar dust, Mars dust contains perchlorates, making it chemically toxic, in addition to being physically problematic. Let's talk about those perchlorates. Perchlorate compounds, particularly calcium perchlorate, are abundant in Mars soil. Measurements from the Phoenix lander found concentrations of about 0.5% by weight. That might not sound like much, but it's everywhere mixed throughout the regolith. Perchlorates are toxic to humans. They interfere with thyroid function by blocking iodine uptake. Chronic exposure can cause hypothyroidism, affecting metabolism, energy levels, and overall health. They're also powerful oxidizers, meaning they can react explosively with organic materials under the right conditions. Any agriculture on Mars would have to deal with perchlorate-contaminated soil. You can't just scoop up Mars dirt and plant crops in it. The soil would need to be washed extensively to remove the perchlorates, requiring large amounts of water, which is scarce on Mars. And the wash water would then be contaminated with perchlorates and would need to be treated before it could be reused. Every spacesuit returning from outside would be covered in perchlorate-laden dust. Removing this dust before entering habitats would be critical but difficult. You'd need airlocks with extensive dust removal systems. Vacuums, brushes, air jets, all trying to clean suits that are covered in electrostatically charged particles that don't want to let go. And despite best efforts, some dust would always get inside. Astronauts would be breathing low levels of it constantly. The long-term health effects of chronic low-level perchlorate exposure aren't fully known because we don't have data on people living in perchlorate-rich environments for years, but it's unlikely to be good. Now let's talk about water. Water is essential for life. Humans need about 2 to 3 L per day just for drinking. Add in water for cooking, hygiene, washing clothes, and you're looking at tens of litres per person per day. For agriculture, the amounts increase dramatically. Growing food requires irrigation. The exact amount depends on what you're growing and how efficient your systems are. But even with the most advanced hydroponics or aeroponics, you need water. On Earth, we take water for granted. It falls from the sky, it flows in rivers, it sits in lakes and oceans. When water is contaminated or consumed, the natural water cycle replenishes it. Rain, evaporation, rivers, groundwater, it all cycles. Mars has no water cycle. There is water on Mars, frozen in the polar ice caps, and probably frozen underground in the regolith at higher latitudes. The polar ice caps are a mixture of water ice and frozen carbon dioxide dry ice. Extracting water from them would require travelling to the poles, which are extremely cold even by Mars standards. Mining the ice, separating the water ice from the dry ice and transporting it back to wherever your habitat is. That's assuming your habitat isn't at the poles, which it probably shouldn't be because temperatures there are even more extreme than at the equator. Alternatively, you could try to extract water from the regolith. At higher latitudes, maybe 30 degrees north or south, and poleward, there's probably water ice mixed in the soil a few centimetres below the surface. You'd have to excavate the soil, heat it to release the water, condense the water vapour and purify it. This requires energy, lots of it, for heating and processing, and you'd need to do this continuously because unlike on Earth, there's no rain to refill your reservoirs. Every drop of water used has to be extracted through this energy-intensive process. In practice, closed-loop water recycling would be essential. Every drop of water would need to be captured, filtered, purified and reused. Wastewater from sinks, showers, toilets, of it would go through extensive treatment and recycling. The International Space Station already does this. Astronauts drink recycled urine and sweat. The system recovers about 93% of the water. The remaining 7% is lost mostly as vapour that escapes or is chemically bound in waste product. On Mars, you'd need similar or better systems, but that 7% loss adds up. If a colony of 100 people uses 50 L of water per person per day, that's 5,000 L per day total. Losing 7% means 350 L per day needs to be replaced. That's 127,000 L per year that has to be mined and processed from Martian ice or regolith. 127,000 L is 127 metric tons of water, assuming it's pure. That's a lot of ice to mine and a lot of energy to process. And this is just for 100 people with basic needs, no agriculture. If you want to grow food, the water requirements multiply. Let's talk about food. Humans need about 2,000 to 2,500 calories per day. In space or on Mars, where physical work is demanding and environmental stress is high, that number might be higher. Astronauts on the ISS consume about 2,500 to 3,500 calories per day. Let's assume 3,000 calories per person per day. For 100 people, that's 300,000 calories per day. Over a year, that's about 110 million calories. Now, you can't ship food from Earth indefinitely. Launch costs are too high and cargo capacity is limited. A SpaceX Starship, the vehicle currently being developed for Mars missions, might carry 100 metric tons of cargo to Mars. That sounds like a lot until you realize that freeze-dried food has an energy density of about 400 to 500 calories per 100 G. Let's say 450. To supply 100 people with 1 to 110 million calories per year, you need about 24,000 kg or 24 metric tons of freeze-dried food per year. A single Starship cargo load might supply 100 people for about 4 years if the entire cargo is food. But you also need equipment, spare parts, building materials, scientific instruments, medical supplies. Food can't be the only cargo. So realistically, initial missions would carry maybe a year or two of food, and then the colony has to become self-sufficient. Growing food on Mars is possible in theory. You'd build pressurized greenhouses, bring soil or grow media from Earth, or manufacture it from Mars, regolith after extensive cleaning and treatment, provide artificial lighting or use sunlight and grow crops. But the challenges are immense. First, the light. Mars receives about 43% of the sunlight that Earth does because it's farther from the sun. This is enough 50 to 100 square meters of growing space per person to provide a complete diet depending on crop choices and efficiency. For 100 people, that's 5,000 to 10,000 square meters, about 1 to 2 acres. That's a massive greenhouse, or more likely multiple greenhouses. Each greenhouse needs to be pressurized to Earth-like pressure, about 100 times the outside pressure. This means the structure has to withstand enormous stress with the inside pushing out against the near vacuum outside. It's like a balloon that's constantly trying to burst. The structural engineering for large pressurized transparent structures is extremely difficult. Windows or transparent panels have to be strong airtight and resistant to the temperature extremes and radiation on Mars. They also have to allow light through, which means you can't shield them with meters of regolith like you would for habitats, so the greenhouses would be exposed to high radiation levels. Plants are somewhat more radiation resistant than animals, but they're not immune. High radiation can damage plant DNA, reduce growth rates, and decrease yields. You might need to rotate crops more frequently or accept lower yields than you'd get on Earth. And the plants themselves wouldn't be the only concern. Humans would need to enter the greenhouses to tend the crops. Every hour spent in a radiation-exposed greenhouse is another dose of radiation for the farmers. You could build the greenhouses underground with artificial lighting, only solving the radiation problem, but massively increasing the energy requirements because now you're providing 100% artificial light instead of using sunlight. Either way, the energy costs are substantial. Let's talk about energy. Energy is the foundation of everything on Mars. Heating habitats, pressurizing structures, recycling air and water, growing food running computers, communications, scientific equipment, manufacturing, repair, construction, everything requires energy. On Earth we have abundant energy sources. Fossil fuels, although problematic for climate, are energy dense and easy to use. Renewable energy from wind, solar, and hydroelectric is increasingly viable. Nuclear power provides dense, reliable energy. On Mars, the options are limited. Fossil fuels don't exist. Mars never had the ancient biological activity necessary to create coal oil or natural gas. Wind power is nearly useless. The thin atmosphere means wind, even strong wind, carries very little energy. The force of wind is proportional to air density. With 1%, the atmosphere of Earth wind on Mars has 1% the force. A 100 mph wind on Mars has the force of a 1 lph breeze on Earth. Nowhere near enough to turn a turbine effectively. Hydroelectric power requires flowing water. Mars has no rivers, so realistically you're left with solar and nuclear. Solar power on Mars is viable but challenging. As mentioned, Mars receives 43% of Earth's sunlight. Solar panels on Mars would generate about 43% of what they would on Earth, assuming the same efficiency. But efficiency on Mars would likely be lower due to dust accumulation. Mars has global dust storms that can last for months. During a major dust storm, the sky darkens and sunlight drops dramatically. The Opportunity rover, which ran on solar power, was lost during the 2018 global dust storm, when its panels couldn't generate enough electricity to keep it alive. For a human colony, relying solely on solar power is risky. You'd need massive energy storage systems to survive dust storms that could last weeks or months. Batteries at that scale would be incredibly heavy to transport from Earth and difficult to manufacture on Mars. Nuclear power is more reliable. A nuclear reactor provides constant power regardless of whether day or night storm or clear skies. The challenges are transporting the reactor to Mars, which requires heavy shield at threshold we don't know. It's possible that Mars' gravity is enough to prevent the worst effects. It's also possible that it's not, and colonists would still experience bone loss, muscle atrophy, and cardiovascular deconditioning just slower than in zero-G. If it takes 6 months to get to Mars and you spend that time in zero-G during the flight, you'll arrive at Mars with weakened bones and muscles. Then you'll spend years in 0.38G, possibly weakening further. If you ever wanted to return to Earth, would your body be able to readapt to 1G? After years in lower gravity, returning to Earth might be like an Earth person suddenly experiencing 2.6 times Earth's gravity. Everything would feel crushingly heavy. Your bones, weakened from years of low gravity, might not be able to support your weight. You might suffer fractures just from standing up. Your heart, deconditioned from years of easier pumping, might struggle to circulate blood against full Earth gravity. This is all speculation because we don't have data. But it's a terrifying possibility that colonists might become permanently adapted to Mars and unable to ever return to Earth. You would be stuck on Mars for life, not by choice but by physiology. And then there's the question of children. If a colony is truly going to be self-sustaining, people will have children. What happens to a fetus developing in 0.38G? What happens to a child growing up in low gravity? Human bones develop and strengthen in response to stress from gravity and physical activity. A child growing up on Mars would experience much less gravitational stress. Would their bones develop properly? Would they reach normal bone density? We have no idea. It's entirely possible that children born and raised on Mars would have fragile skeletons, unable to withstand Earth gravity. They might be taller than Earth humans because their spines aren't compressed as much, but with weaker bones that break easily. Their muscles might be weaker because they never had to work against full gravity. Their hearts might be smaller and less powerful. If a Mars-born child ever came to Earth, they might struggle with the gravity, unable to stand without support, their bones too weak to handle the increased weight. Again, this is speculation, but it's based on what we know about how bodies respond to mechanical stress, and it's a real risk that we won't understand until someone actually tries it. Which brings us to one of the most disturbing ethical questions. Is it right to have children on Mars when we don't know if they'll develop normally? When there's a real chance they'll be biologically trapped on Mars, unable to ever visit the planet where their species evolved? These are questions we'll have to answer, and the answers aren't easy. Now let's talk about the psychological challenges. Living on Mars would be psychologically brutal. You're confined to small habitats most of the time because going outside requires a spacesuit and carries risks. The Martian environment is actively hostile, constantly trying to kill you through radiation, cold vacuum, and toxic dust. You're millions of miles from Earth with communication delays of between 4 and 24 minutes, depending on the orbital positions of the planets. If you need help, there is no help. If there's an emergency, you handle it yourself, or you're gone. Resupply missions from Earth only come every 2 years during the windows when the planets are properly aligned. If you run out of something critical, you wait 2 years or you improvise. The psychological stress of this environment would be immense. We have some data from Antarctic research stations, which are the closest Earth analogue. People who spend months at isolated Antarctic bases experience stress depression, interpersonal conflicts, and sometimes severe psychological breakdowns. And those people know they can leave. They can call home with minimal delay. They can be evacuated in an emergency. They're still on Earth. On Mars, you can't leave except during the 2-year windows when the planets align. You can't call home for a real conversation because of the communication delay. You can't be evacuated if you have a serious mental illness on Mars when psychiatric care is limited and evacuation isn't an option. These aren't hypothetical concerns, they're problems that would absolutely happen and that a Mars colony would have to deal with. And then there's the return trip problem. Getting to Mars is hard but doable with current technology. Getting back is harder. A spacecraft going from Earth to Mars can use Earth's atmosphere for aerobraking, slowing down by friction with the Martian atmosphere to save fuel. Mars' thin atmosphere makes this less effective than aerobraking at Earth, but it helps. To leave Mars and return to Earth, you need to launch from the surface, which requires a rocket. Building and fueling a rocket on Mars is a major challenge. You need to bring the rocket components from Earth, which adds to the cargo you're sending. And you need to manufacture rocket fuel on Mars. The most promising approach is to use Mars's atmospheric carbon dioxide and water ice to make methane and liquid oxygen through chemical processes. This is called in situ resource utilization. It's theoretically possible, but it requires significant equipment and energy. You need to extract water, electrolyze it into hydrogen and oxygen, react the hydrogen with carbon dioxide from the atmosphere, to make methane, liquefy the methane and oxygen and store them. All of this requires power, reliable equipment and time. If any step fails, you can't make fuel and you can't leave. And even if you successfully make fuel and launch the return trip to Earth, takes 6 to 9 months, same as the outbound trip. During that time, you're in 0G, again experiencing all the health problems that come with microgravity. When you arrive at Earth, you'll have been in low gravity for potentially years, and you'll need to readapt to 1G. For older colonists, or those who spent many years on Mars, this might not be possible. Their bodies might have degraded too much, so the return trip is not guaranteed to be safe, and for some people, it might not be survivable. Now let's talk about the economic reality. Colonizing Mars would be staggeringly expensive. Estimates vary wildly, but serious analysis suggests that establishing a self-sustaining colony of even a few hundred people would cost hundreds of billions to trillions of dollars. The initial missions would cost tens of billions each. Developing the spacecraft landers' habitats, power systems, life support rovers, and all the other equipment would cost billions before the first mission even launches. Each launch to Mars would cost hundreds of millions at minimum, even with reusable rockets like Starship. And you'd need many launches. Dozens of cargo missions to preposition equipment, habitats and supplies, then crew missions to transport people, then regular resupply missions every 2 years. The costs add up quickly. And there's no economic return. Mars has no resources that are valuable enough to justify the transportation cost to bring them to Earth. There's no Martian product you could sell on Earth that would pay for the shipping. Bringing gold from Mars would cost more than the gold is worth. There's talk of Mars being valuable for scientific research, which is true. But scientific research doesn't generate profit. It's funded by governments or philanthropists because we value knowledge, not because it makes money. A Mars colony would be a permanent money sink. It would require continuous funding from Earth to survive. As soon as the funding stops, the colony is in trouble. This is fundamentally different from historical colonization on Earth. When Europeans colonized the Americas, the colonies could become economically self-sufficient. They had land resources and eventually trade. They could support themselves and even become profitable. A Mars colony cannot become economically independent from Earth because there's nothing on Mars to sell that would pay for the supplies from Earth that the colony needs. So the colony is permanently dependent on whoever is funding it, whether that's a government, a corporation, or a wealthy individual. If the funder loses interest, has a financial crisis, or simply decides the colony isn't worth the cost anymore, the colony is in existential danger. You can't just abandon a Mars colony without consequences. The people there would be stranded. But maintaining a colony indefinitely for decades or centuries without any economic return requires a level of sustained commitment that's difficult to imagine. Governments change priorities. Corporations care about profits. Even wealthy philanthropists are mortal. What happens when the person or institution funding a Mars colony decides to stop? This is one of the most unsettling realities of a Mars colony. It is not self-sustaining economically, and it might never be. It would always be dependent on Earth, vulnerable to political changes, economic downturns, or shifts in public opinion. And if support from Earth stops, everyone on Mars is facing a slow crisis as resources dwindle and systems fail. Now let's address the common counter-arguments. People often say that the challenges are just engineering problems that can be solved with enough effort and money. That's partially true. Many of the technical challenges are solvable in principle. We can build radiation shielding, we can develop better life support systems, we can design more efficient habitats. But some problems aren't just engineering challenges, they're fundamental physical constraints. You can't engineer away the fact that Mars' gravity is 0.338 g. You can't change the fact that Mars has no magnetic field. You can't give Mars a thicker atmosphere without terraforming on a scale that would take thousands of years and technology we don't have. Some aspects of Mars colonization run up against limits that aren't solvable with better engineering. They're limits imposed by physics and biology. Another argument is that we need a backup for humanity in case something happens to Earth. Asteroid, impact, nuclear war, climate catastrophe, pandemic, any number of existential risks could threaten life on Earth. Having a self-sustaining colony on Mars would mean humanity survives, even if Earth becomes uninhabitable. This argument has emotional appeal, but it's flawed in several ways. Air, tolerable pressure, some water, and moderate temperatures compared to Mars. Climate catastrophe, Earth, even with severe warming, would still be far more livable than Mars. An Earth with a massive asteroid impact, even a dinosaur killer, would recover over time and would still have more resources and better conditions than Mars. The idea that Mars is a safer backup than Earth is questionable. Second, a Mars colony wouldn't be truly independent from Earth for a very long time, possibly centuries. It would depend on Earth for supplies, equipment, genetic diversity, and knowledge. If Earth suffered a catastrophe that destroyed industrial civilization, the Mars colony would lose its supply line and would likely fail. So Mars doesn't work as a backup unless it's completely self-sufficient, which brings us back to all the challenges we've discussed. Third, resources required to establish a Mars colony are so vast that they could arguably be better spent making Earth more resilient to threats. Mars. Some people argue that exploring and colonizing space is part of human nature, that we're explorers, and will eventually spread to other planets regardless of the challenges. This is true in a sense. Humans are curious and ambitious. We've explored every corner of Earth, climbed the highest mountains, reached the poles, descended to the deepest oceans. We've gone to the moon. We'll certainly send humans to Mars at some point for exploration and scientific research. But exploration is different from colonization. You can explore Mars without establishing a permanent colony. Temporary research stations like we have in Antarctica are one thing. Permanent self-sustaining settlements are something else entirely. And just because we can do something doesn't mean we should. We could try to colonize the bottom of the ocean, but we don't because the challenges outweigh the benefits. Mars might fall into the same category. Interesting to visit, valuable for science, but not practical for permanent habitation. Now let's consider the timeline. Even if we solve all the technical problems, how long would it take to establish a real colony? Optimistic projections from people like Elon Musk suggest the first crewed missions to Mars could happen in the late 20s or early 30s. Let's assume that happens, that we successfully land humans on Mars by 2030. That's just the first mission. They'll stay for a few months, do some science and return to Earth. Building up to a permanent presence with even a few dozen people would take additional missions over many years. Each mission is constrained by the 2-year windows when Earth and Mars are aligned. So realistically, you might build up to a small outpost with 10 to 20 people by the early 40s. Scaling up to 100 people, which is often cited as the minimum for a viable colony with enough genetic diversity and skill diversity, might take until the 50s or 60s, and that's assuming everything goes well. No major setbacks, consistent funding, and rapid technological progress. More realistic timelines accounting for likely delays, budget constraints, and technical problems might push these dates back by decades. We might not see a 100-person colony until the late 21st century. And even then, it wouldn't be truly self-sufficient. It would still depend heavily on Earth. Achieving real independence where the colony could survive indefinitely without any support from Earth might take another century of development on Mars. We're talking about a project that spans multiple human lifetimes. Generations of people would need to maintain the commitment, the funding, and the effort. That's a huge ask. Consider also the opportunity cost. The resources spent on Mars colonization could be spent on other things. Fusion energy research, curing diseases, addressing poverty and inequality, combating climate change, exploring and protecting our oceans, advancing AI and biotechnology. All of these could have more immediate and tangible benefits for humanity than a Mars colony. This isn't to say Mars colonization has no value. It does. Scientific knowledge, technological development inspiring future generations, these are real benefits. But we have to weigh them against the costs and against the alternative uses of those resources. And when you do that calculation honestly, it is not clear that Mars colonization is the best use of our limited resources, at least not in the near term. Let's talk about something we haven't covered yet, the journey to Mars itself. Getting to Mars isn't like taking a flight across the ocean. It's a 6 to 9 month journey through interplanetary space depending on the trajectory and the propulsion system. During this time, astronauts are confined to a spacecraft that's essentially a tin can travelling through the void. The psychological challenges of the journey alone are significant. You're in a small space with the same few people for months. You can't go outside. You can't call home for a real conversation because of communication delays. You're constantly aware that between you and the vacuum of space is just a thin metal wall. And you're getting farther from Earth every day, moving into a region of space where no human has ever been. The spacecraft has to be completely self-sufficient during the journey. Life support has to work perfectly for months. Any failure could be fatal. Water recycling, air recycling, temperature control all have to function flawlessly. Spare parts for critical systems have to be on board because there's no way to get more. The astronauts have to carry all their food for the journey, 6 to 9 months of freeze-dried meals. The same limited menu over and over, no fresh food, no fresh vegetables, just whatever, can be packaged and stored. The monotony alone would be psychologically challenging. Then there's the radiation exposure during the journey. In interplanetary space, you're outside Earth's protective magnetic field. Cosmic rays hit the spacecraft constantly. Solar particle events can deliver dangerous doses of radiation over hours. The spacecraft needs shielding, but shielding is heavy, and every kilogram you add to the spacecraft requires more fuel to push it to Mars. There's always a trade-off between protection and practicality. Current spacecraft designs for Mars missions include some shielding, but it's not enough to reduce radiation to Earth-like levels. Astronauts on the journey would receive significant radiation doses, adding to the dose they'll receive on Mars's surface. By the time they arrive, they've already accumulated months of radiation exposure, and their cancer risk has already increased. There's also the issue of exercise. In 0G, your muscles and bones don't have to work against gravity. Without intervention, they atrophy rapidly. Astronauts on the International Space Station exercise for about 2 hours per day to maintain muscle mass and bone density. Even with that much exercise, they still lose some strength and bone mass. On a Mars journey, even when personal feelings get in the way. Now let's talk about what happens when they arrive at Mars. The landing itself is one of the most dangerous parts of the whole mission. Mars' atmosphere is thick enough to cause heating during entry, requiring a heat shield. But it's thin enough that it doesn't slow you down as much as Earth's atmosphere would. You're travelling at thousands of miles per hour and you need to slow down to a safe landing speed using a combination of atmospheric drag parachutes and retro rockets. This is called the 7 minutes of terror in NASA parlance. It's the time from when the spacecraft hits the top of the atmosphere to when it lands. During those 7 minutes, everything has to work perfectly. The heat shield has to protect against temperatures of thousands of degrees. The parachutes have to deploy at exactly the right time and altitude. The retro rockets have to fire correctly. The landing legs have to absorb the impact. Any failure at any step means crashing into the surface at high speed, and during those 7 minutes there's a communication delay of 4 to 24 minutes between Mars and Earth. So mission control can't help. They won't even know if the landing succeeded until several minutes after it's over. The spacecraft is on its own following pre-programmed sequences. We've gotten pretty good at landing robotic spacecraft on Mars, but landing humans is different. The spacecraft is much bigger and heavier. It needs more fuel, bigger parachutes, more powerful rockets, and the margin for error is smaller because human lives are at stake. A robotic mission that crashes is a loss of money and scientific data. A crewed mission that crashes is a loss of human life. The psychological pressure on the crew during landing would be intense. They're passive passengers at that point. The spacecraft's computers are in control. They just have to sit there and hope everything works. If it does, they're on Mars. If it doesn't, they have seconds to react, and there's probably nothing they can do. Assuming they land safely, they're now on the surface of Mars with limited supplies and a hostile environment. The first task would be to set up life support and power. They'd need to deploy solar panels or activate a nuclear reactor. Set up the habitat modules, pressurize them, and make sure everything is working. All of this would be done in spacesuits because the habitat isn't ready yet. Working in a spacesuit on Mars is exhausting. The suits are bulky and restrictive. Every movement requires effort because you're working against the pressure of the suit. Your hands get tired quickly because the gloves are stiff. You overheat because the suit's cooling system can only do so much, and you're constantly aware that any rip or puncture could be fatal. Simple tasks that would take minutes on Earth take hours in a suit on Mars. Astronauts on the Moon during Apollo missions found that working in suits was one of the physically demanding things they'd ever done. And Mars has more gravity than the Moon, which means more weight to carry around, which means more effort. The first days and weeks on Mars would be a race against time. They'd need to get the habitat functional, verify that life support is working, set up communications with Earth, and begin surveying the surrounding area for resources. And they'd need to do all of this before their consumables run out. They'd arrive with a limited supply of oxygen, water, and food brought from Earth. Those supplies would last weeks or months depending on how much cargo capacity the mission had. During that time, they'd need to get systems online to produce oxygen from the Martian atmosphere, extract water from the soil or ice, and start growing food. If any of those systems fail, they're in trouble. They can't just order a replacement part from Earth. They'd have to improvise repair or do without. This is where the crew's skills become critical. You'd need people with expertise in engineering, biology, medicine, geology, chemistry, and more. Each person would need to be competent in multiple areas because the crew is small and every role is essential. If the biologist is the only one who knows how to run the greenhouse, and they get injured or sick, someone else needs to be able to take over. Cross-training would be essential, but it adds to the pre-mission training burden. The crew would need years of training before the mission, learning not just their primary jobs, but backup roles as well. Let's talk about manufacturing and repair. On Earth, if something's it yourself or improvise a replacement, You can't print a new solar panel or a new battery. Some things have to be brought from Earth as spares, and if you run out, you're stuck. This is one of the reasons why a Mars colony would need to be large enough to support some manufacturing capability. With 100 people, you might have enough expertise and labour to set up workshops, refine raw materials, and manufacture simple parts. With 10 people, you're much more limited. Everything has to be brought from Earth or improvised on a very basic level, scaling up manufacturing on Mars to the point where the colony can make most of what it needs would take decades, and would require a steady flow of equipment and materials from Earth during that time. You'd need mining equipment to extract iron ore, aluminum ore, and other metals. You'd need smelters to refine the ores. You'd need machine shops to work the metals. You'd need chemical plants to produce plastics, glass, and other materials. All of this requires energy, lots of it, which brings us back to the power problem. A serious industrial base on Mars would need far more than one MW. You'd need tens of MW, maybe more. That means multiple nuclear reactors or vast solar arrays, and all of this has to be built up gradually, step by step over many years. The early colony would be almost entirely dependent on Earth. Over time, with sustained effort and investment, it could become more self-sufficient. But true independence, where the colony doesn't need anything from Earth, is a very long-term goal. We're talking 50 to 100 years minimum, possibly longer. Now let's talk about medical care. Medical emergencies on Mars are a nightmare scenario. On Earth, if you have a heart attack, you call an ambulance. Paramedics arrive within minutes. You're at a hospital within an hour. Doctors run tests, perform surgery if needed, and you have access to the full range of modern medical technology. On Mars, if you have a heart attack, you're dependent on whoever's with you and whatever medical supplies are available. The best case is that one of your crewmates is a trained doctor with surgical experience. Even then, the medical facilities would be limited. You'd have a small medical bay with basic equipment, bandages, antibiotics, pain medication, some diagnostic tools like an ultrasound machine or a portable X-ray, but nothing like a full hospital, no MRI machines, no extensive pharmacies with hundreds of medications, no blood bank, no organ transplant capability. If you need surgery, it would be performed in the small medical bay by whoever has the most medical training. If you need a blood transfusion, you'd better hope someone in the crew has a compatible blood type and is willing to donate. If you need a medication that's not in stock, you improvise or do without. For routine medical issues, a Mars colony could probably manage. Broken bones infections, cuts and bruises, these can be treated with basic medical knowledge and supplies. But serious medical emergencies, heart attacks, strokes, appendicitis, major trauma, these would be life-threatening in ways they aren't on Earth. Appendicitis is a good example. On Earth, it's a routine emergency. Get to a hospital, a surgeon removes your appendix, you recover in a few weeks. The mortality rate is very low, less than 1%. On Mars, if you develop appendicitis, you need surgery quickly, or you could be gone within days as the appendix ruptures and infection spreads. If you have a trained surgeon in the crew and they can perform the appendectomy, you'll probably be okay. If you don't have a surgeon, someone with less training would have to attempt it and the risk goes up significantly. Or you could try treating it with antibiotics and hoping it resolves without surgery, which works sometimes, but not always. There's also the issue of medical knowledge degradation. A doctor who trained on Earth but hasn't performed surgery in years might forget key skills. Medical knowledge requires practice to maintain. On Mars, with a small population, medical emergencies would be rare. A doctor might go years without performing certain procedures. When a real emergency happens, their skills might be rusty. They'd be working from memory and whatever medical references they have, hoping they remember the correct procedure. This is a real concern in any isolated environment. Antarctic research stations deal with it by rotating medical staff regularly and providing telemedicine support from specialists on the mainland. On Mars, telemedicine would have the communication delay problem. A doctor on Earth could watch a video of the surgery and provide advice, but there would be a 4 to 24-minute delay between sending the video and receiving the response. That's workable for routine consultations, but not for real-time surgical guidance. If something goes wrong during surgery, the Mars doctor is on their own. There's also the issue of pharmaceuticals. Medications have expiration dates. Most remain effective for some time after the official expiration, but potency decreases. On a Mars colony, medications would age. The antibiotics you brought might be less effective after a few years. The pain medications might not work as well, and manufacturing new pharmaceuticals on Mars would be incredibly difficult. Most modern drugs are complex organic molecules that require sophisticated chemistry to produce. You need specialized equipment, pure reagents, and expertise. A small Mars colony wouldn't have pharmaceutical manufacturing capability. They'd be dependent on drugs brought from Earth. As those drugs age and lose effectiveness, the colony's medical capabilities would degrade unless regular resupply missions bring fresh medications. Then there's the issue of medical emergencies during the journey. If someone has a heart attack during the 6 to 9 month flight to Mars, what do? There's no turning back. Earth is millions of miles away. Mars is millions of miles ahead. You're stuck in the spacecraft with limited medical facilities. The crew's medic would do their best, but the outcome is uncertain. If the patient survives the initial event, they'd arrive at Mars with a heart condition. Are they still capable of the physical work needed to establish a base? If not, you've now got a crew member who can't pull their weight, which puts more burden on everyone else. This is a harsh reality, but it's one that mission planners would have to consider. Crew selection for Mars missions would need to account for health very carefully. Only the healthiest individuals with no chronic conditions or genetic predispositions to disease would be selected. Even then, accidents and acute illnesses can happen to anyone. Let's talk about what happens if someone is gone on Mars. If a crew member passes during the mission, whether from accident, illness, or any other cause, what do you do with the body? On Earth we have burial or cremation. On Mars, neither is straightforward. Burial requires digging, which is difficult in the frozen regolith. You'd need powered equipment to excavate a grave. And there's a question of whether burying human remains in Martian soil is acceptable from a planetary protection perspective. We try to avoid contaminating Mars with Earth biology, and human bodies are full of Earth bacteria. Cremation requires fuel and produces emissions. On a resource-limited colony, burning fuel to cremate a body might seem wasteful, and the emissions would need to be captured or vented, which could pose problems. Some have suggested that in the far future bodies could be processed for useful materials. The water content could be reclaimed. The organic material could be composted for agriculture. This is brutally pragmatic, but on Mars resources are so scarce that waste is a luxury you can't afford. Experience. The cultural and psychological gap between Earth and Mars would grow over time. Colonists might develop their own slang, their own traditions, their own way of thinking. They might start to see themselves as Martians rather than as Earth people living on Mars. This could be the beginning of a separate Martian identity. Anthropologically, this would be fascinating, but it would also create potential for conflict or misunderstanding between Earth and Mars. Different priorities, different values, different perspectives. Let's consider the legal and governance questions. Who has authority on Mars? Is it NASA if it's an American mission? Is it a consortium of space agencies from multiple countries? Is it a private company like SpaceX? Current space law, primarily the Outer Space Treaty of 1967, says that no nation can claim sovereignty over celestial bodies. Mars doesn't belong to any country, but it also says that countries are responsible for their nationals' activities in space. So if American astronauts are on Mars, the US government has some responsibility and authority. But what does that mean in practice? Can the US impose laws on Mars colonists? Do they need to follow American law? What if the colony includes people from multiple countries whose laws apply? And if a private company like SpaceX establishes the colony, does the company have authority? Can they set rules for colonists? These questions don't have clear answers yet. They'd need to be worked out through international agreements and probably new treaties, but governance on Mars is complicated by the communication delay. If there's a dispute or emergency on Mars, contacting Earth for instructions means waiting hours for a response. In a real crisis that's not workable, the colonists would need to make decisions on their own. This means Mars would need some form of local government or decision-making structure. Maybe a council of colonists, maybe a designated leader, maybe some form of democracy. But whoever is making decisions would be doing so with limited oversight from Earth. They'd have de facto autonomy just because of the communication delay. Over time, this could lead to Mars becoming politically independent from Earth, whether officially or not. If Earth tries to impose rules that the colonists don't like, the colonists might simply ignore them. What is Earth going to do? Send police to Mars? That's not practical, so Mars colonists would have a degree of freedom that could lead to interesting political developments. They might experiment with new forms of governance, new social structures, new ways of organizing society. Or they might recreate the same political systems that exist on Earth. It depends on who the colonists are and what their values are. Now let's talk about the ethical implications of colonizing Mars. One argument against colonization is planetary protection. Mars might have its own microbial life. We don't know. We haven't found it yet. But absence of evidence isn't evidence of absence. Mars has liquid water underground in some areas. It has organic compounds in the soil. It had a thicker atmosphere and liquid water on the surface billions of years ago. If life ever started on Mars, it might still exist in sheltered underground environments. If we colonize Mars, we'll inevitably contaminate it with Earth life. Bacteria from our bodies, from our equipment, from our waste. We can sterilize things to some degree, but we can't eliminate all microbes. Humans are walking ecosystems. We carry trillions of bacteria on our skin, in our guts, in our mouths. When humans go to Mars, those bacteria go too. If there is Martian life, Earth, life might outcompete it, contaminate it, or hybridize with it in ways we can't predict. We might destroy the very thing we're hoping to study. This is a real ethical concern. Some scientists argue that we should fully explore Mars robotically, first searching for life before we send humans. Once humans are there, the planet is contaminated and we lose the ability to study it in its pristine state. Others argue that humans are necessary for serious exploration, and that the benefits outweigh the risks. Minerals, who owns them, who profits from mining them under the Space Treaty's celestial bodies, are the province of all mankind. But in practice, if a company mines asteroids or Mars, they'd probably claim ownership of what they extract. This could lead to a new kind of colonialism, where wealthy companies or nations exploit space resources while others are left out. There's a risk of repeating the patterns of Earth's colonial history, where powerful entities took resources from less powerful ones. Avoiding this would require international cooperation and agreements on resource sharing. Whether that's achievable is uncertain. Then there's the question of who gets to go to Mars. The first missions will be highly selective. Only the most qualified, healthiest, most capable individuals will be chosen. This makes sense from a mission success perspective, but it also means that Mars colonization, at least initially, is only for the elite. If space travel becomes more accessible over time, maybe ordinary people could go. But in the near term, it's astronauts, scientists, engineers, the best of the best. There's something uncomfortable about the idea that Mars is only for the privileged few. It's humanity's dream, but only certain humans get to pursue it. This might seem like a minor point, but it reflects broader issues of equity and access. Who gets to shape humanity's future in space? Is it everyone, or just those with the resources, skills, and opportunity? These are questions we'll need to grapple with as space exploration expands. Now let's talk about something we touched on earlier but deserves more attention. Dust storms. Mars is famous for its dust storms, and they're not like anything on Earth. Earth's dust storms in places like the Sahara or the American Southwest are bad enough. They reduce visibility, ground flights, damage equipment, and cause respiratory problems. But they're localized and they pass relatively quickly, usually within hours or days. Mars dust storms can be global. They can cover the entire planet and they can last for months. In 2018, a global dust storm covered Mars for several months. The sky darkened so much that the Opportunity rover, which had been operating for almost 15 years, lost power because its solar panels couldn't generate electricity. NASA tried to wait out the storm, hoping Opportunity would recharge once the skies cleared. But the rover never responded again. It likely lost so much power that its internal clock failed, and it couldn't reorient its solar panels toward the sun even after the storm ended. All the dust that accumulated on its panels was too thick to shake off, or the extreme cold during the months without power damaged critical components. Whatever the reason, Opportunity was gone. For a human colony, a global dust storm would be a major crisis. If you're relying on solar power, your electricity generation drops dramatically. The atmosphere turns orange-brown with dust. Sunlight levels drop to a fraction of normal. Solar panels might generate 10 or 20% of their usual output, maybe less. This means you need massive battery reserves or another power source like nuclear. Without sufficient power, life support systems start to fail. Heating becomes insufficient and habitats get cold. Air slows down and carbon dioxide builds up. Water recycling stops and you start depleting reserves. All the systems you depend on require power, and a months-long dust storm would push those systems to the limit. Even with a nuclear reactor providing baseline power, you'd likely need to ration electricity. Non-essential systems get shut down. Greenhouse lighting reduced. Scientific equipment powered off. Communications limited to essential messages. Everybody conserving energy however possible. And then there's the dust itself. Mars dust is incredibly fine, finer than talcum powder. Individual particles are only micrometers across. During a dust storm, this fine dust gets everywhere. It infiltrates seals, coats, solar panels, gets into mechanical joints, scratches optics. The dust is also electrostatically charged because of friction in the atmosphere. This makes it stick to surfaces. You can't just blow it off, it clings. On the Apollo missions, lunar dust was a huge problem, and lunar dust is similar to Mars dust in texture and electrostatic properties. Astronauts found it impossible to keep dust out of the lunar module. It got on their suits during moonwalks and came inside with them. It got into seals, into electronics, into the lungs. Several astronauts reported respiratory irritation from inhaling tiny amounts of dust. On Mars, during a months-long dust storm, keeping dust out of habitats would be nearly impossible. Every time someone goes outside and comes back in, they bring dust with them. Over time, the interior of the habitat would become contaminated. Colonists would be breathing low levels of dust constantly. And remember, Mars dust contains perchlorates, which are toxic. Long-term exposure to perchlorate dust would cause health problems. Thyroid issues, as mentioned earlier, but also potential damage to lungs and other organs. Air filtration systems would need to work overtime, and filters would need frequent replacement. If you run out of filters, air quality deteriorates. The mechanical problems caused by dust would compound over time. Rovers and vehicles would experience accelerated wear. Seals on airlocks would degrade faster. Hinges and joints would become gritty and stiff. Solar panel efficiency would drop permanently as scratches accumulate on the glass surface. Every dust storm would take a toll on equipment, shortening its operational lifespan. And unlike on Earth, where you can order replacement parts on Mars, you'd have to make do with what you have or wait years for resupply. Dust storms also affect visibility. During a storm, you can't see far. The dust in the air scatters light, creating a brown haze. This makes outdoor work more difficult and dangerous. Navigation becomes harder. If you're out in a rover and visibility drops, you might get lost. GPS doesn't exist on Mars yet, and dead reckoning in low visibility is risky. You could drive into a crater or ravine that you can't see until it's too late. The psychological effect of dust storms shouldn't be underestimated either. Imagine looking out your habitat window and seeing nothing but orange-brown haze for months. No horizon, no sky, no sun, just oppressive dusty gloom. The darkness and monotony would be mentally exhausting. Seasonal affective disorder affects people on Earth who don't get enough sunlight during winter. On Mars, during a global dust storm, everyone would be experiencing something similar: depression, lethargy, sleep problems, mood swings. And this would be happening while the colony is also dealing with power shortages and equipment problems, stress on top of stress. Now, let's discuss the biological adaptation challenges in more depth. We talked about bone and muscle loss in low gravity, but there are other biological effects we need to consider. The human immune system functions differently in space. Studies on astronauts show that immune response is suppressed during spaceflight. This makes sense from an evolutionary perspective. The immune system evolved in Earth's gravity and atmospheric conditions. Change those conditions and the system doesn't work as efficiently. Astronauts on the International Space Station are more susceptible to infections. Viruses that are dormant in the body, like herpes simplex, sometimes reactivate during long space missions. Wounds heal more slowly. The thymus gland, which produces immune cells, atrophies in microration for every preventable disease. Strict hygiene protocols, isolation of sick individuals. But in a small colony, isolation is difficult. You can't just send sick people to another building. Space is limited. Another biological concern is the effect of low gravity on pregnancy and fetal development. As we mentioned, we have no data on this, but it's reasonable to expect problems. Fetal development is a complex process where cells differentiate and organize into tissues and organs. Gravity provides mechanical cues that influence this process. Bone formation, muscle development, the cardiovascular system. All of these are shaped partly by gravitational forces. In low gravity, these developmental processes might go wrong. Skeletal abnormalities, weak muscles, heart defects, neurological problems. We don't know what would happen, but the risks are real. And there's no way to find out without actually having pregnant women on Mars, which raises enormous ethical issues. Is it ethical to allow pregnancy on Mars when the child might be born with severe health problems? Do the potential colonists have the right to make that choice for themselves and their unborn children? Or should there be a moratorium on pregnancy until we understand the risks better? These are deeply personal and ethically complex questions. Some people would argue that reproduction is a fundamental human right and can't be restricted. Others would argue that bringing a child into the world with a high risk of serious health problems is irresponsible. And if children are born with health problems on Mars, can they be treated? Medical care for congenital conditions often requires specialized equipment and expertise. Heart surgery on a newborn, for example, is incredibly complex and requires a team of specialists. That's not available on Mars. A child born with a correctable heart defect on Earth might be doomed on Mars. This is a heartbreaking scenario that colonists would have to consider. Let's talk about the comparison with Earth's harshest environments. Some people argue that if humans can survive in Antarctica or the Sahara or the deep ocean, we can survive on Mars. But this comparison doesn't hold up. Antarctica is harsh, yes. Temperatures drop to 130 degrees Fahrenheit in winter. It's isolated, dry and hostile, but Antarctica has breathable air. You can step outside without a spacesuit, just warm clothing. If your heating fails, you can survive for a while by burning fuel, wearing layers and staying active. If you run out of food, there's wildlife. You could hunt seals and penguins, though that's not ideal. If you have a medical emergency, you can be evacuated. Planes can reach Antarctic research stations in hours or days, weather permitting. You're isolated, but you're still on Earth. Rescue is possible. Mars offers none of these fallbacks. The atmosphere will kill you in minutes. There's no wildlife to hunt. There's no rescue coming from Earth. You're on your own in a way that's incomparable to anywhere on Earth. The Sahara Desert is hot, dry, and hostile. But it has air. It has some water if you know where to look. It has life insects, reptiles, plants. If you're stranded in the Sahara and you're resourceful, you might survive until rescue arrives. On Mars, if you're stranded outside your habitat, you have the air in your suit, maybe a few hours worth, and that's it. No water source nearby, no shade from the sun's radiation, no possibility of rescue if your suit fails. The deep ocean is another comparison people make. Humans have reached the deepest parts of the ocean in submersibles. The pressure is crushing, the darkness is total, the cold is extreme. But the ocean is on Earth. If something goes wrong, you can surface. Rescue submarines can be sent, you can be back on land in hours, and the ocean is full of life. Even at the deepest depths, there are fish microbes, ecosystems. Mars has none of that. It's sterile, cold, airless, and radiation-soaked. The comparison doesn't work. Mars is qualitatively different from anywhere on Earth. It's not just harder or more extreme. It's a different category of hostile. Some people argue that technology makes up the difference. That spacesuits and habitats give us the protection we need. But technology fails. Seals crack. Electronics malfunction. Power systems fail. On Earth, when technology fails, you have fallbacks. Natural air, water, moderate temperatures. On Mars, when technology fails, you're gone. There's no natural backup. You're entirely dependent on systems working perfectly all the time forever. That's a level of vulnerability that humans have never experienced before. Even on the International Space Station, which is the closest analogue we have, astronauts can evacuate in a Soyuz capsule and be back on Earth within hours if there's an emergency. On Mars, there's no evacuation. You're stuck there for years until the next launch window. And if things are bad enough that evacuation seems necessary, waiting 2 years might not be an option. This brings us to perhaps the most sobering aspect of Mars colonization, the permanence. Once you're there, you're there. For years, at minimum, possibly for life. If you change your mind, if you get homesick, if the psychological stress becomes too much too bad, you can't leave until the planets align, and even then, leaving might not be safe depending on your health and how adapted your body has become to Mars gravity. This is different from any other human migration in history. When Europeans sailed to the Americas, the journey was dangerous and took months. But once you arrived, you could theoretically turn around and go back. It was difficult, but possible. When people move to remote locations on Earth today, they can leave if things don't work out. You can quit your job in Antarctica and fly home. You can leave the Sahara Research Station. You can surface from the deep ocean. On Mars, you're committed to what we do. We explore. We push boundaries. We seek new horizons. From this perspective, Mars colonization is about the human spirit, about our drive to explore and grow. It's about ensuring that humanity doesn't remain confined to one planet forever. It's about taking the next step in our evolution as a species. This is a powerful idea, but it's also abstract. It doesn't put food on the table or cure diseases or address the very real problems we face on Earth. And that's where the debate gets difficult. We limited resources, limited time, limited attention. Do we invest heavily in Mars colonization, or do we focus on Earth's problems? Climate change, poverty, disease, political instability, environmental degradation. These are urgent issues that affect billions of people right now. Shouldn't we solve these first before we worry about colonizing other planets? Or can we do both? Can we address Earth's problems while also pursuing space exploration? Maybe. But resources are finite. Money spent on Mars missions is money not spent on renewable energy, healthcare, education, or infrastructure. This isn't to say Mars colonization is wrong. It's to say that it's a choice, and choices have opportunity costs. We need to be honest about what we're prioritizing and why. For some people, the dream of Mars is worth the cost. It represents hope, ambition, and the best of human aspiration. For others, it's a distraction from more pressing concerns, a vanity project for billionaires while Earth burns. Both perspectives have validity, and maybe the answer isn't one or the other. Maybe we can pursue Mars exploration in a measured way. Robotic missions continue. We learn more about Mars, its resources, its challenges. We develop the technology gradually. And if in the future the technology improves to the point where colonization becomes more feasible and less risky, we can pursue it then. But we don't rush into it now with our current limitations. Don't send people to Mars prematurely and watch them struggle or fail because we weren't ready. We take our time, do it right, and make sure that when we do send people, they have the best possible chance of success and survival. That seems like a reasonable middle ground. Explore Mars, absolutely. Learn from it, study it, appreciate it, but colonize it only when we're truly ready, when the technology is mature, when the risks are minimized, and when we've thought through the ethical implications. Not because a billionaire wants to see it in his lifetime. Not because of nationalistic pride or corporate profit, but because humanity as a whole has decided it's the right next step, and we've done the work to ensure it can be done safely, sustainably, and responsibly. The terrifying problem with colonizing Mars is that the challenges are far more severe than most people realize. Radiation exposure that would give you cancer. A toxic environment that would kill you in minutes without protection. Extreme cold. No air. No water cycle. No food chain. Weak gravity that might your body over time. Psychological isolation that would test your sanity. Economic dependence on Earth that makes true independence nearly impossible. And all of this compounded by the fact that Mars is millions of miles away, making resupply difficult and rescue impossible. These aren't minor obstacles, they're fundamental problems that don't have easy solutions. Some might not have solutions at all within the constraints of current physics and biology. This doesn't mean we'll never send people to Mars. We probably will for short-term missions, scientific research and exploration. But the dream of large, thriving independent colonies of Mars as a true second home for humanity, that might remain a dream. At least with anything resembling current technology and understanding. Maybe in the far future with technologies we can't yet imagine it becomes possible. Advanced genetic engineering that makes humans more radiation resistant and better adapted to low gravity. Artificial gravity systems that we don't know how to build yet. Fusion power that makes energy abundant and cheap. Breakthroughs in materials science that make construction on Mars far easier. Advances in AI and robotics that automate most of the difficult work. With those kinds of advances, maybe Mars colonization becomes feasible. But those are speculative future technologies. With what we have now and what we're likely to have in the next few decades, Mars colonization remains extraordinarily difficult and dangerous. The people who go to Mars, especially in the early missions, will be taking enormous risks. They'll be pioneers in the truest sense, facing an environment that's trying to kill them every moment of every day. Some of them won't come back, whether by choice or because something goes wrong. That's the reality we're facing. It's not impossible. Humans have done impossible things before, but it's far harder, far more dangerous and far less certain than the optimistic visions often portrayed. An understanding that really understanding the depth of the challenges is important. Because if we're going to do this, if we're going to commit the resources and the lives necessary to establish a presence on Mars, we should do it with our eyes open, knowing exactly how hard it will be, knowing exactly what we're asking people to sacrifice, and knowing that despite all our efforts, it might not work. That's the honest truth about colonizing Mars. It's a dream that might be beyond our reach, or at the very least beyond our reach for far longer than we'd like to admit. And maybe that's okay. Maybe Mars is meant to be visited, studied, and appreciated from a distance rather than colonized. Maybe our efforts are better spent taking care of the one planet we know can support us. Earth. The pale blue dot that for all its problems is still the most welcoming place in the known universe for human life. Because when you really look at the challenges, when you honestly assess what we're up against, you start to appreciate just how precious and rare Earth is. Every breath of air you take without thinking about it, every sip of water, every moment you spend outside without a spacesuit, every sunrise and sunset, the rain, the wind, the seasons, the life all around you, all of it is something Mars can never give us. Not naturally, not without enormous effort and artificial systems that could fail at any moment. Mars is a magnificent world in its own right. It deserves to be explored and studied. But it's not Earth. And maybe, just maybe, the dream of colonizing Mars should make us appreciate Earth more. should make us more committed to protecting this planet, to solving its problems, to ensuring it remains habitable. Because in the grand scheme of things, Earth is far easier to save than Mars is to colonize, and that's a truth worth remembering. Thanks for staying with me through this long journey into the reality of Mars colonization. The terrifying problems are real,